factors. The transistor channel resistance does not change, while gate capacitance is cut by that factor. Hence the RC delay of the transistor scales with a similar factor. While this has been traditionally the case for the older technologies, for the state-of-the-art MOSFET's reduction of the transistor dimensions does not necessarily translate to higher chip speed because the delay due to interconnections is more significant. Producing MOSFETs with channel lengths much smaller than a micrometer is a challenge, and the difficulties of semiconductor device fabrication are always a limiting factor in advancing integrated circuit technology. Though processes such as ALD have improved fabrication for small components, the small size of the MOSFET, less than a few tens of nanometers, has created operational problems. Higher subthreshold conduction. As MOSFET geometries shrink, the voltage that can be applied to the gate must be reduced to maintain reliability. To maintain performance, the threshold voltage of the MOSFET has to be reduced as well. As threshold voltage is reduced, the transistor cannot be switched from complete turn-off to complete turn-on with the limited voltage swing available. The circuit design is a compromise between strong current in the on case and low current in the off case, and the application determines whether to favor one over the other. Subthreshold leakage, including subthreshold conduction, gate oxide leakage and reverse-biased junction leakage, which was ignored in the past, now can consume upwards of half of the total power consumption of modern high-performance VLSI chips. 3940. Increased gate oxide leakage. The gate oxide, which serves as insulator between the gate and channel, should be made as thin as possible to increase the channel conductivity and performance when the transistor is on and to reduce subthreshold leakage when the transistor is off. However, with current gate oxides with a thickness of around 1.2 nm, which in silicon is 5 atoms thick, the quantum mechanical phenomenon of electron tunneling occurs between the gate and channel, leading to increased power consumption. Silicon dioxide has traditionally been used as the gate insulator. Silicon dioxide, however, has a modest electric constant. Increasing the dielectric constant of the gate dielectric allows a thicker layer while maintaining a high capacitance. Capacitance is proportional to dielectric constant and inversely proportional to dielectric thickness. All else equal, a higher dielectric thickness reduces the quantum tunneling current through the dielectric between the gate and the channel. Insulators that have a larger dielectric constant than silicon dioxide, referred to as high dielectrics, such as group IVB metal silicates, for example half-Newman zirconium silicates and oxides, are being used to reduce the gate leakage from the 45 nanometer technology node onwards. On the other hand, the barrier height of the new gate insulator is an important consideration. The difference in conduction band energy between the semiconductor and the dielectric, and the corresponding difference in valence band energy, also affects leakage current level. For the traditional gate oxide silicon dioxide, the former barrier is approximately 8 eV. For many alternative dielectrics, value is significantly lower, tending to increase the tunneling current, somewhat negating the advantage of higher dielectric constant. The maximum gate source voltage is determined by the strength of the electric field able to be sustained by the gate dielectric before significant leakage occurs. As the insulating dielectric is made thinner, the electric field strength within it goes up for a fixed voltage. This necessitates using lower voltages with the thinner dielectric. Increased junction leakage. To make devices smaller, junction design has become more complex, leading to higher doping levels, shallower junctions, halo doping and so forth. 41, 42, all to decrease drain-induced barrier lowering. See the section on junction design. To keep these complex junctions in place, the annealing steps formerly used to remove damage and electrically active defects must be curtailed. 43. Increasing junction leakage. Heavier doping is also associated with thinner depletion layers and more recombination centers that result in increased leakage current, even without lattice damage. Drain-induced barrier lowering, DIB, and VT roll-off. Because of the short channel effect, channel formation is not entirely done by the gate, but no, the drain and source also affect the channel formation. As the channel length decreases, the depletion regions of the source and drain come closer together and make threshold voltage, VT, a function of the length of the channel. This is called VT roll-off. VT also becomes function of drain to source voltage, VDS. As we increase the VDS, the depletion regions increase in size, and a considerable amount of charge is depleted with VDS. The gate voltage required to form the channel is then lowered, and thus, the VT decreases with an increase in VDS. This effect is called drain-induced barrier lowering, DIB. Lower output resistance for analog operation. Good gain requires a high MOSFET output impedance, which is TOSE. The MOSFET current should vary only slightly with the applied drain to source voltage. As devices are made smaller, the influence of the drain competes more successfully with that of the gate due to the growing proximity of these two electrodes, increasing the sensitivity of the MOSFET current to the drain voltage. To counteract their resulting decrease in output resistance, circuits are made more complex, either by acquiring more devices, for example the cascode and cascade amplifiers, or by feedback circuitry using operational amplifiers. For example, a circuit like that in the adjacent figure. Lower transconductance. The transconductance of the MOSFET decides its gain and is proportional to hole electron mobility, depending on device type, at least for low drain voltages. As MOSFET size is reduced, the fields in the channel increase and the dopant impurity levels increase. Both changes reduce the carrier mobility, and hence the transconductance. As channel lengths are reduced without proportional reduction in drain voltage, raising the electric field in the channel, the result is velocity saturation of the carriers, limiting the current and transconductance. Interconnect capacitance. Traditionally, switching time was roughly proportional to the gate capacitance of gates. However, with transistors becoming smaller and more transistors being placed on the chip, interconnect capacitance, the capacitance of the metal layer connections between different parts of the chip, is becoming a large percentage of capacitance. 44, 45, signal shave to travel through the interconnect, which leads to increased delay and lower performance. Heat production. The ever-increasing density of MOSFETs on an integrated circuit creates problems of substantial localized heat generation that can impair circuit operation. Circuits operate more slowly at high temperatures, and have reduced reliability and shorter lifetimes. Heat sinks and other cooling devices and methods are now required for many integrated circuits, including microprocessors. Power MOSFETs are at risk of thermal runaway. As their on-state resistance rises with temperature, if the load is approximately a constant current load, then the power loss rises correspondingly, generating further heat. When the heat sink is not able to keep the temperature low enough, the junction temperature may rise quickly and uncontrollably, resulting in destruction of the device. Process variations. With MOSFETs becoming smaller, the number of atoms in the silicon that produce many of transistors' properties is becoming fewer, with the result that control of dopant number sound placement is more erratic. During chip manufacturing, random process variations affect all transistor dimensions, length, width, junction depths, oxide thickness, etc., and become a greater percentage of overall transistor size as the transistor shrinks. The transistor characteristics become less certain, more statistical. The random nature of manufacture means we do not know which particular example MOSFETs actually will end up in a particular instance of the circuit. This uncertainty forces a less optimal design because the design must work for a great variety of possible component MOSFETs. See process variation. Design for manufacturability, reliability engineering, and statistical process control. 46. Modeling challenges. Modern ICs are computer simulated with the goal of obtaining working circuits from their very first manufactured lot. As devices are miniaturized, the complexity of the processing makes it difficult to predict exactly what the final devices look like, and modeling of physical processes becomes more challenging as well. In addition, microscopic variations in structure due simply to the probabilistic nature of atomic processes require statistical, not just deterministic, predictions. These factors combine to make adequate simulation and right the first time manufacture difficult. Other types. Dual gate. The dual gate MOSFET has a tetrode configuration, where both gates control the current in the device. It is commonly used for small signal devices in radio frequency applications where biasing the drain side gate at constant potential reduces the gain loss caused by Miller effect, replacing two separate transistors in cascode configuration. Other common uses in RF circuits include gain control and mixing, frequency conversion. The tetrode description, though accurate, does not replicate the vacuum tube tetrode. Vacuum tube tetrodes, using a screen grid, exhibit much lower grid plate capacitance and much higher output impedance and voltage gains than triode vacuum tubes. These improvements are commonly in order of a FinFET magnitude, 10 times, or considerably more. Tetrode transistors, whether bipolar junction or field effect, do not exhibit improvements of such a great degree. The FinFET is a double-gate silicon-on insulator device, 1 year for number of geometries being introduced to mitigate the effects of short channels and reduce drain-induced barrier lowering. The fin refers to the narrow channel between source and drain. A thin insulating oxide layer on either side of the fin separates it from the gate. SOI FinFET with a thick oxide on top of the fin are called double gate, and those with a thin oxide on top as well as on the sides are called triple gate FinFET. 47, 48. Depletion mode. There are depletion mode MOSFET devices, which are less commonly used than the standard enhancement mode devices already described. These are MOSFET devices that are doped so that a canal exists even with zero voltage from gate to source. To control the channel, a negative voltage is applied to the gate, for an N-channel device, depleting the channel, which reduces the current flow through the device. In essence, the depletion mode device is equivalent to a normally closed, on, switch, while the enhancement mode device is equivalent to a normally open, off, switch. 49. Due to their low noise figure in the RF region, and better gain, these devices are often preferred to bipolar in RF front ends such as in TV sets. Depletion mode MOSFET families include BF960 by Siemens and Telefunken, and the BF980 in the 1980s by Philips, later to become NXP semiconductors, whose derivatives are still used in AGC and AF mixer front ends. Metal insulator semiconductor field effect transistor, MOSFET. Metal insulator semiconductor field effect transistor, 50, 51, 52, or MOSFET, is a more general term than MOSFET and a synonym to insulated gate field effect transistor, IGFET. All MOSFETs are MISFETs, but not all MISFETs are MOSFETs. The gate dielectric insulator in a MOSFET is silicon dioxide in a MOSFET, but other materials can also be employed. The gate dielectric lies directly below the gate electrode and above the channel of the MOSFET. The term metal is historically used for the gate material, even though now it is usually highly doped polysilicon or some other non-metal. Insulator types may be silicon dioxide, in MOSFETs. Organic insulators. For example, undoped transpolyurethione, cyanidylpullulane, CEP, 53, for organic-based FETs. 52. MOS logic. For devices of equal current driving capability, N-channel MOSFETs can be made smaller than P-channel MOSFET, due to P-channel charge carriers, holes, having lower mobility than do N-channel charge carriers, electrons, and producing only one type of MOSFET on a silicon substrate is cheaper and technically simpler. These were the driving principles in the design of MOS logic, which uses N-channel MOSFET exclusively. However, neglecting leakage current, unlike MOS logic consumes power even when no switching is taking place. With advances in technology, MOS logic displaced NMOS logic in the mid-1980s to become the preferred process for digital chips. Power MOSFET. Cross-section of a power MOSFET, width square cells. A typical transistor is constituted of several thousand cells. Power MOSFETs have a different structure. 54, as with most power devices. The structure is vertical and not planar. Using a vertical structure, it is possible for the transistor to sustain both high blocking voltage and high current. The voltage rating of the transistor is a function of the doping and thickness of the N-epitaxial layer, see cross-section, while EV current rating is a function of the channel width. The wider the channel, the higher the current. In a planar structure, the current and breakdown voltage ratings are both a function of the channel dimensions, respectively width and length of the channel, resulting in inefficient use of the silicon estate. With the vertical structure, the component area is roughly proportional to the current it can sustain, and the component thickness, actually the N-epitaxial layer thickness, is proportional to the breakdown voltage. 55. Power MOSFETs with lateral structure are mainly used in high-end audio amplifiers and high-power PA systems. Their advantage is a better behavior in the saturated region, corresponding to the linear region of a bipolar transistor, than the vertical MOSFETs. Vertical MOSFETs are designed for switching applications. 56. Double diffused metal oxide semiconductor, DMOS. There are DMOS, lateral double diffused metal oxide semiconductor, and VDMOS, vertical double diffused metal oxide semiconductor. Most power MOSFETs are made using this technology. Radiation hardened by design, RHBD. Semiconductor submicrometer and nanometer electronic circuits are the primary concern for operating within the normal tolerance in harsh radiation environments like outer space. One of the design approaches for making a radiation hardened by design, RHBD, device is enclosed layout transistor, ELT. Normally the gate of the MOSFET surrounds the drain, which is placed in the center of the ELT. The source of the MOSFET surrounds the gate. Another RHBD MOSFET is called H-gate. Both of these transistors have very low leakage current with respect to radiation. However, they are large in size and take more space on silicon than a standard MOSFET. In older STI, shallow trench isolation designs, radiation strikes near the silicon oxide region cause the channel inversion at the corners of the standard MOSFET due to accumulation of radiation-induced trapped charges. If the charges are large enough, the accumulated charges affect STI surface edges along the channel near the channel interface, gate, of the standard MOSFET. Thus the device channel inversion occurs along the channel edges and the device creates off-state leakage path, causing device to turn on. So the reliability of circuits degrades severely. The ELT offers many advantages. These advantages include improvement of reliability by reducing unwanted surface inversion at the gate edges that occurs in the standard MOSFET. Since the gate edges are enclosed in ELT, there is no gate oxide edge, STI at gate interface, and thus the transistor off-state leakage is reduced very much. Low-power microelectronic circuits including computers, communication devices and monitoring systems in space shuttle